All right. Inverses. Turn to a neighbor and answer the question, what are we talking about when we say inverses? What does that make you think of?
The numerator? The opposites. Oh my gosh, it's gross.
So if y'all would graph like this, I guess, and then I just
Okay, thoughts, inverses, what do we remember?
inverse.
The opposite, flip,
It's like the same thing. It's like
reverse, okay?
Flip the X.
Flip the X and the Y. Okay, yeah, so that's a huge part of it, is switching X and Y. So this function right here, it's pretty easy to find the inverse of that. We literally just switch the X and Y coordinates. And that would be the inverse. But yeah, inverse functions are functions that are basically opposites of each other. Functions that undo each other. Yeah, basically what that means is we're switching X and Y. Okay, when you have two functions that are inverses of each other, they are reflections of each other over the line.
Origin.
Not over the origin. Over the line.
Symmetry.
There's a line of symmetry. What would that line be? What would the equation of that line be? Y equals X. Ah, reflections about the line Y equals X. There it is right there.
I didn't see it.
So these two functions right here, this red one and purple one up here, we can see visually that they're inverses of each other because they look like they've been reflected over this line, which is Y equals X. The connection being that if we switch X and Y, it's like we're saying, okay, what if Y equaled X? And so they reflect over that line, Y equals X. We've talked about some inverses before this year. We talked about like sine and sine inverse as an example. We also talked about these two functions pictured right here. What does this red one look like? What kind of function is that? What's that? Normal function? You could be more specific. What do we think this red function is? What does it look like?
X cubed plus.
It's not cubed.
Is it a fraction?
It's not a fraction.
It's not X squared.
It's not X squared.
The square root of X plus 2. It's not.
It's not a square root.
1 over X minus 2.
All right. Yikes, you guys. So it looks to me like, well, I'm going to estimate a little bit. If I have this point 0, 1, 1, 2, maybe 2, 4. I'm getting powers of 2 here. 1, 2, 4, 8, 16. This kind of looks like it's 2 to the x.
Yeah, I remember seeing this place.
Okay, yeah. Standard 5. We graph those. We did transformations, move them around. And so we also talked about the inverse of 2 to the x. What's the inverse of an exponential function? What's that? Logarithm, close. Logarithm, yes. This would be log 2 of x. Remember that this represents the number that turns 2 into x. So when we graph these, we were talking about like, okay, well, 2 could turn into 1, 2, 4, or 8. Those are the powers that it turns into. And the exponent that would do that is 0, 1, 2, 3. But notice those are inverses of each other. We have the x and y values switched. And we see that symmetry right here. Yeah. So that's the other example that we talked about earlier this week. We're going to look at finding inverses. But first, we are going to talk a little bit about this right here. This is something you would have talked about last year in Algebra 2. So we have this term, one-to-one. If a function is one-to-one, that means that it is a function and its inverse is a function. And we can tell if it's a function because it passes the what test? The vertical line test. Okay, so this is a function, this is a function. We can tell if the inverse is a function if it passes the horizontal line test. So would the inverse of this one be a function? Does that pass the horizontal line test? Yes. Yes. So this one, the inverse, again, the inverse would look like a reflection over the line y equals x. It would look like that. Does that graph pass the vertical line test? Yeah, it does. So by looking at the original, we can tell if it would pass, if the inverse would pass the vertical line test, if it passes the horizontal line. We're switching x and y, everything that was vertical is going to become horizontal, and vice versa. When functions are one-to-one, it makes finding the inverse a lot easier. Would we say that this graph here is one-to-one? No, because it what?
As it's not reflected.
Because it doesn't pass the horizontal line test. It fails the horizontal line test, which means, again, it is a function, true or false? True. The inverse is a function, true or false? False. Okay. When I take the inverse, when I reflect it, like that, we can see, oh yes, the inverse for sure fails the vertical line test. That is not a function. This is going to cause us some problems when we find the inverse of x squared. And let me illustrate that. So the inverse of x squared is this. These are inverses of each other. Does anyone know what the equation of the inverse would be? Square root of x? Square root of x, that is close. Square root of x looks like this. This is square root of x. Ooh, plus or minus square root of x. Yes. That is correct. And that basically has to do with the shape. X squared is a parabola. Plus or minus square root x is not a function, but it is a parabola. Would you agree? It's just going sideways. Okay. The function square root of x is not a parabola. How would you describe it? Half of a parabola, which means that the inverse of square root of x also needs to be half of a parabola. So the inverse of square root of x looks like this. And the equation of this one is a little strange. It would be y equals x squared with domain 0 to infinity. So basically saying it's like we have the full parabola, but then we cut it in half. We only allow half of it to exist so that these two can be inverses of each other. So, quick recap. If a function is one-to-one, if it passes the horizontal line test, we're going to be able to find the inverses basically with no problems. If a function is not one-to-one, like a parabola, finding the inverse is going to be a little tricky because we need to make sure that things have the same shape. And we'll look at examples where that's going down. So to find the inverse of a function, we do this process. We write it as y equals, we switch x and y, we then solve for y, and then we rewrite it as f inverse of x, and I'll add a fifth step here. We'll think about the shape. And mostly we'll have to do that for problems like these. Just like that. Okay, so for this first problem here, problem A, to find the inverse, step 1. Right, it is y equals. Okay, so y equals 8x minus 3. Just replace that f of x with y. Nice. And then switch x and y. So we've got x equals 8y minus 3. And then solve for y. How do we solve for y here? Add 3 to both sides. Divide by 8. And then our last step, well, fourth step. Yes. Okay. So there's our inverse. Nice. And then step 5, we're going to think about the shape. So what shape does our original function make? What would that look like? One of these. A line, right? Y equals mx plus b, 8x minus 3. Okay, so this is a line, slope of 8, y-intercept negative 3, up 8 over 1, etc. What shape does our inverse make? A line, yeah. If the first one's a line, the inverse should be a line. What is the slope of our inverse? 1/8. What's the y-intercept?
3 over 8.
3 over 8. Yeah, the 8 goes to both. The 8 divides to both. We distribute it. 1/8 x plus 3/8. Just a little, algebra review. So those are two shapes. They're the same shape, right? They're both lines. The original one passes the horizontal line test. Function's one-to-one. Means when we find the inverse, we're not really going to run into any problems. Do those two graphs appear to be inverses of each other? Does it look like we reflected over the line y equals x? Which would go like right there? Yeah, I'd say so. Nice. Okay, again, if it's like a line, we're not going to have any problems. Okay. Letter B, step 1. Right as y equals. Step 2. Switch x and y. Step 3. Solve for y. How do we solve for y? Square both sides. And then subtract 5. Divide by 2. And then write it as f. And the way that we say that is f inverse of x. Okay. Step 5, think about the shape. What shape is our original function? It's a square root function like that. A parabola? Half of a parabola, okay? This original one kind of looks like this. Kind of looks like that one right there. Which way has it been shifted? 5 to the
5 to the left.
5 to the left. Okay, it's actually it's 5/2 to the left, but it is shifted to the left. Well, we have to factor out the 2. But yeah, it's shifted to the left. Is it shifted up or down? No, it's not. There is a horizontal compression going on. That's what the 2's doing. That doesn't really matter for the shape. Like, it's still half a parabola. It's shifted to the left. Okay. Currently, our inverse. Whoa, what shape is our inverse? A parabola. Okay. Right now, these are not the same shape, because what shape do we need to make our inverse into? Half of a parabola. Okay. Which way is our parabola shifted? Five halves, which way? To the left? To the right?
Down.
To the up? To the down? We said all directions. Which one is it?
To the diagonal. Diagonal.
It shifted down.
Oh, I said that.
Yeah, you said all of them. Right? This is, when we're subtracting outside of x, that means we're going down. Option to yell timber. Our parabola is going down. Okay? So and just down, right? Not left or to the right. I guess I'm just going to tell you it's not going to the left or to the right because we don't seem super confident. But I'll tell you, it's not to the left or the right. It's just going down. Where would we cut this thing in half so that the shape matches? What x value? 0, yes. The halfway point is at 0. We would say, okay, we're going to say the domain of this parabola is now just 0 to infinity. We are manually cutting it in half when we write that. Yes, we have to do it. Otherwise, they're not inverses. We need them to be the same shape. Okay. Yeah. We know that x squared forms parabola shapes. And we know that square root x forms half parabola shapes. We should. Okay. A shortcut for domain. The domain of the inverse, and that's going to matter for any half parabola, is the same as the blank of the original. The range, yeah, because we're switching what things with an inverse? X and Y, right? So range is all the Y values, domain is all the X values. Domain and range are going to flip as well. So sometimes this can help us find that domain. So this is like the next level of inverse stuff is you have to think about the shape, and sometimes we have to put in domain restrictions. This is the main type of problem that we're going to see with that. Parabolas and half parabolas. We're going to keep it pretty straightforward, but we'll think about that. Let's go to the next page.
Oh.
Okay. So here's something that's true. Two functions, f of x and g of x, are inverses of each other if f of g of x equals x and g of f of x equals x. If we do the composition and they basically just cancel each other out, and we're just left with x, that means they're inverses of each other. So this is how we prove if two functions are inverses. So for number 6, prove whether f of x and g of x are inverses, we would have to do f of g of x and hope it equals x. and g of f of x. So why don't you guys do that? We'll see what happens. Okay. So we do f of g of x 2 times 1/2 x plus 3 minus 6. How do we simplify that? What do I do first? Distribute. So that's x plus 6 minus 6, which equals? Nice. Okay. We don't have to worry about domain for this. In this case, it's all real numbers, but like you don't have to do what we were doing on the warm-up where you find the domain in 2 places. We're just doing this to prove whether or not they're inverses. Okay. If one of them equals x, like if we do f of g of x and we get x as a result, it means the other one should also equal x. And it should do that every time. So if you don't get x on the second one, it means you just made a mistake somewhere. So it's a good way to check. You do have to do both of them because it's a proof. But the result of the first one will let you know what the result of the second one should be. They should agree with each other. So we do 1/2 2x minus 6 plus 3. Distribute the 1/2. We get x minus 3 plus 3, which equals x. Okay. So these things are inverses of each other. We need to do one more thing to finish this. We need to say in words, in a little sentence, that they are inverses and why. So we say f of x and g of x are inverses of each other because f of g of x equals g of f of x, which equals x. And that's like the shortest version of that we can write. Yes, you have to do this on the quiz and the test. Questions? Okay. Number 7. Are these functions inverses? Explain graphically and algebraically. When we say algebraically, we are talking about composition. That means the same thing. We have our equations right there, so we could do composition with those two things. When it says explain graphically, it means look at the graph and say, basically, do they look like they're inverses? Does it appear that they're inverses? What would you guys say? Why? They do appear, as much as we can tell, to be reflected over this line, y equals x or x equals y. So graphically, you're not going to be able to give like a definite answer. It's more going to be like, yeah, probably. It's the composition that would actually prove it. Unless you had like a list of all the points and could see that the x's and y's were. Well, I want to go on to number 8, but I just wanted to point that out. So you can't really prove it graphically. You could just quickly say like, oh yeah, it looks like it. Or no, definitely not. Okay, number 8. What do we got going on here? Turn to your partner and talk about it. What is that? What's all that?
That just needs to be half.
One of them is
Oh, wait. Yeah. Well, then I don't know. Oh my God, I was just confused. Well, then I don't really know what to ask.
Okay, what's going on here? What do we got?
One,
Oh, yeah,
they're
that
both x minus 4, but one squared goes square rooted.
Okay. Yeah. What else can we say about this? What do we got? What's going on here?
The top's a half parabola and the bottom's a parabola, but the number is squared, so it's only using half.
Okay. So would you say that both of them are half parabolas? Okay. Would you guys agree with that? They're both half parabolas? Yes. Okay. I agree. Which means that they could be inverses of each other because they're the same shape. Could be inverses. Have the same shape. Just half parabola. Not saying they are. Okay. If that domain restriction was not there, we would have a half parabola and what? A parabola. Could those be inverses of each other? No, they could not. They're different shapes. We wouldn't even have to do the composition. We would just say these functions are different shapes. They're not inverses of each other. So we're including that in there so that the question's even possible. Okay, prove algebraically. What does that mean again? Composition. Cool. Do it. Do it. Okay, are these inverses of each other? No, they're not. So we do f of g of x, and that's square root of x squared minus 4 minus 4. Square root of x squared minus 8. Does that equal x? Nah, for sure no. We cannot distribute the square roots to addition or subtraction. Okay, that's fully simplified. That's all we can do. We do g of f of x. Okay, if I get something other than x for the first one, that's telling me I should get that for the second one. The results should agree with each other. So I've got root x minus 4 squared minus 4. That squared and square root cancels out. So we just get x minus 4 minus 4, which is x minus 8. Does that equal x? Okay, we still need to say this, f of x and g of x are not inverses of each other. Because of this. F of g of x does not equal g of f of x, which does not equal x. Let's go to the next page. Okay. Moving on to these more complicated functions. Let's think about the shape of this one real quick. I want you guys to try and sketch a graph of this. Here are some things to think about. Vertical asymptote, horizontal asymptote, y-intercept, plug in 0 for x, x-intercept. Talk with your partner about that. Standard 4. Oh, what the? Okay, let's talk about shape. Vertical asymptotes. Think domain for this one. What could x not equal? -3, right? That's where we have a vertical asymptote, not allowed to divide by 0. Horizontal asymptote. 1, yeah. It's you reduce these numbers right there. X over x reduces to 1. This is because as we get really far out to the left and to the right, the bigger x is, the more this number looks like 1. So what's like, if x equals 1,000,000, what's 1,000,006 divided by 1,000,003, roughly? 1. What about 1,000,006 divided by 1,000,003? 1. It's pretty much 1. So eventually this function just goes to 1 on both sides. The y-intercepts, plug in 0 for x, what do we get? What happens when we plug in 0 for x? 2. 6 over 3 is 2. The x-intercepts set the top equal to 0. -6. Okay. Our function looks like this. If anything canceled out on the top and the bottom, we would have a hole in the graph. Okay. Does this function pass the horizontal line test? Yes, it does. Which means that the inverse is also a function. Whoa. Which means that we can just do the inverse without really worrying about the shape. All this to say, we can just take the inverse normally. Is it working? Yeah, we're not going to have to restrict the domain or anything crazy like that. Okay. How to find the inverse? What do we do? First step? Yeah, trade f of x for y. Then switch x to y. Then solve for y. How do we get y by itself? We've seen this before. Huh? No. I guess. I mean, like action. Multiply both sides by x plus 3. X plus 3. Multiply both sides by y plus 3. Break. Okay, that gets y off the bottom. Okay. Subtract the 6.
Divide by.
Divide by x. Divide by y. Trying to get y by itself. Right now it's in a parentheses.
Divide by y.
What'd you say? Subtract 1. Distributes.
Oh yeah, that's your.
Yeah.
Oh my gosh. You were right.
Because we're trying to get y by itself, we need to get it out of the parentheses. Because y is in 2 places. Right? One's stuck inside a parentheses, the other one's off by itself, but we're not solving for y until we get all the y's together.
And then
Divide by y.
divide by.
Yeah. Move the y over to one side and factor it. Oh, okay. So you're saying subtract y to move it over there and subtract 3x. So we would get something like yx minus y equals 6 minus 3x. And then do what? Factor the y out. Oh.
I remember this part now.
Yeah. We've done this before. Yep, we factored out y. And then divide. When did we do this before?
I remember this.
I remember we had some.
No, I tend to go.
I don't know, I forgot I was doing sports doing breakfast.
Not a good habit in math.
No,
When you need to remember all the math you've ever learned at all. Here's one time when we did this with problems like this. Took the natural log of both sides,
I missed that. I really
move it down, distribute, get the x's to one side, factor x out.
Yeah, I missed that.
I probably said something like, "Hey, we're gonna do this again when we do inverses."
It feels like it was last year.
It was last year.
I feel like I learned this in my
It wasn't in ninth grade though, but it was in the fall, which was 2021. Okay, so that's our inverse. Switch x and y. You have to multiply by y to get it off the bottom. You have to distribute x, get the y's to one side, factor it out. Okay, that's our second to last example. Our penultimate example. Okay, there's a problem with number 10 in the notes. There's a problem with A and B. Does anyone know what it is? That's not the problem, although they do appear to be. They are different fonts and different sizes. There's no graphically, that's not the problem. John? A and B are the same. Prove algebraically, use composition. These things are the same thing. They are no difference. Okay. So, which means we don't need to do both. Our last example just got shorter.
So composition as prove algebraically.
Use, okay, that's actually something I'm going to clarify. Use composition and prove algebraically if two functions are inverses are the same thing. In general, composition is not proving something algebraically, it's just doing composition. If you do both, you can prove if something isn't, two things are inverses or not. Okay, so we're going to do our composition. We'll do one together, then you guys will do the other one. F of g of x means plug which one into which one? Yeah, g of x into f of x. So 2x plus 4, there's g plus 4, g minus 2. We don't have to do domain, but we could think about it. X can't equal 1. What would our next step be? Common denominator. Once we find a common denominator, what can we do? Cancel it out. Let's cross it out. Yeah. What's going to go on top of our new fraction?
2x plus 4 plus 4x minus.
Nice. What's going to go on the bottom?
2x plus 4 minus 2x plus 1.
Nice. Okay, maybe we see what's going to happen here. 6x over 6. Yeah. The 4's cancel on top, the 2x's cancel on the bottom. 6x over 6 equals x. Yeah. Okay. Would you look at that? So that means when we do g of f of x, what should happen? It should also equal x. Cool. See if it does. Okay, did we get x when we did this? No?
Yes.
So 2 times f plus 4 over f minus 1. Common denominator. Cancel it out. Get 2x plus 8 plus 4x minus 8 over x plus 4 minus x plus 2. 8's cancel. X's cancel. We also get 6x over 6.
No, but I don't.
Would we be done with this problem? Yeah, we gotta write it. We gotta say f of x and g of x are inverses. Are inverses because f of g of x equals g of f of x equals x. That's the most abbreviated version. You can abbreviate the word because. Because.
Just say yes.
Okay. I'm gonna give you guys the homework. It's pretty short, but there is a problem that I'm gonna change, and I'm gonna add 2 more problems.
Go add more problems to actual problems.
Wait.
Right. That's great. Mine is actually we still have to know how to draw.
You always do that.
That's where the problem
You don't need to be experts in graphing yet, but that's our next unit is graphing.
But like if we just know how to use composition formulas, like we should be okay.
Okay, first change is number 2. Rewrite it to this.
It's no extra.
Oh, so it's no.
Right. So I'm going to change number 2, and then I'm going to add a 9 and 10. So everybody change number 2 to this.
Oh. Oh, okay.
Wait, but there is a 9 and 10.
I was like,
But I'm going to add another 9 and 10.
Oh my god.
wait, so you're gonna do like 9.5 or like 7 or
There's going to be 2 more problems at the bottom of this page. Let's just put it that way. Let's just put it that way. And it's these 2. It's almost like those problems that we were working on for a while about parabolas and half parabolas. It's almost like I need to practice. So make sure you add these 2 at the bottom of the page.
Sweet.